Hi, this is Alex from devstories.eu. NumPy, Episode 1 of 7. The standard Python list is highly flexible, but the moment you try to do math on a million items, you hit a performance wall. You end up paying a massive pointer tax just to multiply numbers together. The solution to this bottleneck is the core engine of Python scientific computing, the ndarray. To understand why the ndarray exists, you have to look at what standard lists do under the hood. A Python list does not store raw numbers, it stores pointers. Each pointer directs the system to a scattered location in memory where a full Python object lives. If you write a standard loop to multiply two sequences of a million numbers, the Python interpreter works extremely hard. For every single item, it fetches the pointer, locates the object, checks its data type to confirm it is actually a number, calculates the math, and stores the new object. Doing this a million times introduces severe overhead. This pointer chasing and type checking cycle is why standard loops are simply too slow for large mathematical operations. The ndarray, which stands for n-dimensional array, drops this flexibility in exchange for raw speed. The n-dimensional part means this object can represent a flat sequence of numbers, a two-dimensional grid, or a complex multidimensional mathematical matrix. Regardless of how many dimensions you define, under the hood it operates on two strict rules. First, it requires homogeneous data types. Every single element in an ndarray must be the exact same type, such as a 64-bit float. Second, it uses a fixed memory size. When you create an ndarray, NumPy reserves a single continuous block of memory. There are no pointers. The raw numbers sit tightly packed next to each other in the system memory. Here is the key insight. Because NumPy knows the exact data type and the exact memory layout, it can completely bypass the slow Python interpreter. When you multiply two ndarrays containing a million numbers, you do not write a loop. You simply write array A multiplied by array B. This process is called vectorization. NumPy takes your command and hands the actual calculation over to precompiled C code. The C code blasts through that continuous block of memory at hardware speeds. It skips the type checking and pointer lookups for individual items because the memory is perfectly uniform. The trade-off for this massive speed boost is structural rigidity. Because the memory is one continuous block, you cannot just append a new number to an ndarray the way you do with a Python list. If you need a larger array, NumPy generally has to allocate a brand new block of memory and copy the old data over. You build the container to the exact size you need, and then you run your operations on the whole block at once. The standard Python list is a collection of isolated objects spread across memory. The ndarray is a dense, uniform block of raw data designed to be processed instantly by optimized C code. If you enjoy these episodes and want to support the show, you can search for devstories.eu on Patreon. That's all for this one. Thanks for listening and keep building.